In this lecture, we continue the study of the forward converter, the input to output relation as a function of the duty cycle, input voltage and transformer ratio has been studied before. It's very close to the one of the buck converter, with the only difference that the transformer ratio is involved in the input to output relation. We will now focus on the study of the transformer, deriving the equations for the magnetizing current, and also understanding which is the behavior of the tertiary winding. That is one of the techniques that are possible to reset the flux and the magnetizing current into the transformer. A possible way to study the schematic of the forward converter is substituting the transformer with three windings with the ideal model of a transformer plus the magnetizing inductance. This has been done here. These three coupled wires represent the ideal transformer, and this inductance is the magnetizing inductance present due to the ferromagnetic core. For this transformer, given these conventions for the currents, IT1 is entering from the dot, IT3 is entering from the dot, and IT2 is exiting from the dot, we can derive the following relations. For the voltages, the secondary voltage is proportional to N2 divided N1. The tertiary winding voltage is proportional to N3 divided N1. And as a consequence, the tertiary voltage is also proportional to the secondary voltage following the N3 divided N2 transformer ratio. It must be said that quite often the N1 and N3 values are equal. However, we will study the general case. For the currents respect this relation. That is N1 times IT1 minus N2 times IT2 plus N3 times IT3 is equal to 0. This is just the equation that derives studying this ideal transformer. An ideal transformer has zero reluctance, and this means that the sum of the voltages, let's say motive forces, is 0. And this is negative because here we are using this different versus for the current. This is exiting from the dot. From this equation, however, we can obtain that, for example, if IT2 is 0, IT3 is equal to minus IT1 multiplied by N1 divided N3. And if IT3 is 0, IT2 is equal to IT1 multiplied N1 divided N2. These are the cases that interest to us, because we will have a current flowing here that will flow in the other side, and when IT2 is 0, we will have a current IT1 and a current IT3. Let's start studying what happens during the on phase for the switch. The switch is on. We can imagine that here we have a short circuit. This voltage is then 0. We will consider the switching current, ISW. There will be a current flowing through the primary winding of the transformer. This current is IT1, and also there will be a current flowing into the magnetizing current. We can surely say that the primary voltage, that is Vp, is just equal to Vi, since this transistor voltage is 0, the on-state voltage drop, we can say it is almost 0. As a consequence, the secondary voltage is N2 divided N1 multiplied Vi. V3 is equal to N3 divided N1 multiplied Vi. But please note that V3 is in this direction. Once we know the tertiary winding voltage, that is V3, we can calculate the voltage drop on the diode D3. This can be calculated as the sum of Vi plus V3, this is VD3, and minus Vi minus V3, and this is equal to minus Vi multiplied 1 plus N3 divided N1. The absolute value is important because it is larger than Vi, than the input, than supply voltage. This tells us that this diode needs to be chosen to sustain more than the supply voltage. This is a stressed diode in this topology. However, in this phase, this is an important note, but the most important thing that we need to understand is that this voltage is negative. It's minus something. This means that the diode is off. Since the diode is off, IT3 is 0. Once we know that IT3 is 0, we can calculate IT1 and IT2. It's better to start from IT2 because since this other side of the converter is on, this voltage is positive, this diode is off, there will be a current flowing in this direction. This current will pass through diode D1, through the inductance L, and will charge the capacitance and will provide the current to the load. In this phase then, IT2 current is equal to the inductor current. Once we know the IT2 current, we can calculate IT1 current. That will come out like N2 divided N1 multiplied IT2. That is, hence IT2 is proportional to the inductance current. And the switch current will simply be the sum of Im plus IT1. What we understand from this discussion is that the magnetizing current here is of no interest for us. The energy flow, the energy transfer from this side to this side is just given by IT1 that causes a current flow in IT2. Im is just, the magnetizing current is just a parasitic effect. This was not the case for the flyback converter. And this is why in this forward converter we say that we actually need a real transformer. We need a transformer able to transfer energy from one side to the other side without storing too much energy into the transformer. This means that we want an almost ideal transformer with very large magnetizing inductance and very small magnetizing current. We can then assume that Im is much smaller than IT1. Which is the value of Im, we can calculate it later. In this slide, we exactly focus on the calculation of the current behavior and voltage behavior. But for the voltages, there is not much to tell because during the on phase of the switch, the voltages are constant for the forward converter. This is not the case for the currents. Assume that the time belongs to the 0t on period. Then we can say that IT2 is the current that flows through the inductance. But since the secondary voltage is positive and it's larger than the output voltage, this current will increase with time, will linearly increase with time. We keep assuming that we are working in the continuous current mode condition. This means that the current in the inductor is never 0. This means that for the current we can write that we will start at t equals 0 from a minimum, that is IT2 minimum. And to this minimum component, we will add up a component that is proportional to the time and inversely proportional to the inductance, and is proportional to Vi multiplied N2 divided N1, that is the secondary voltage, minus the output voltage. Also written as a function of inductance current, like here. For the magnetizing current, we can write this relation. Actually, the voltage drop on the inductance is constant, is Vi, and so we do expect that it increases linearly. It will be then Vi multiplied T divided Lm. The switch current is just the sum of them. In this equation, we are assuming that the current, the magnetizing current at the beginning of the switch phase, on the on phase, is 0. This is actually an assumption, but we will demonstrate that this is the actual case, because this circuit can only work if we reset the transformer energy and then the magnetizing current after every switch of the transistor. This means that after the switch, the magnetizing current must be 0 and will start from 0 in the next phase. The current will then, magnetizing current will then increase. We can obviously calculate the maximum values of this current, that is IT2 T on, that is this equation where T is substituted with T on, and this is the maximum of IT2 current, and it is also the maximum of the IL current. And also we can calculate the maximum of the magnetizing current. We can then plot current and voltage behavior of the forward converter in this graph. It's not that easy to follow. However, in this graph we made some assumptions, that is N2 is smaller than N1. This is quite often the case, since we want to step down the voltage on the output. And in order to make something visible, we assume that N3 is larger than N1, even if we say that very often N3 is equal to N1. We can then plot the currents like IT2 that increases linearly starting from a minimum. IT1 will be smaller than IT2. This is reasonable, since we imagine that the input voltage is larger than the output voltage, and in assuming 100% efficiency or something like that, in order to provide the same power from a voltage supply that is larger than the output voltage, we need a smaller current. This is the green plot. For the magnetizing current, we use the red plot that is starts from 0 and arrives to a certain maximum. We assume that this is a very small value. And finally, the switch current will be the sum of IT1 plus the magnetizing current. For the voltages, the primary voltage is Vi. The secondary voltage will be smaller than Vi, since N2 is smaller than N1. This is the blue curve. The primary voltage is the green plot. For the transistor voltage, it is not shown here, but we assume, let's say, almost 0. We are assuming ideal components, almost 0 voltage. The voltage on the diode, V3, the tertiary winding V3, will be positive and proportional to N3 divided N1. Since we assume that N3 is larger than N1, this is larger than Vi. And finally, the D3 voltage that is negative, okay, but much larger than Vi, for the assumption that we made. These plots are not to scale, obviously. We can keep studying the behavior of the forward converter, studying what happens during the off phase of the switch. This is the situation. The switch is open. There is no current flow through the switch. As a consequence, the voltage drop on this transistor will reverse the voltage on the secondary switch. That will prevent the activation of this diode. The secondary current will then be 0, and for the output, the current regime is just supported by the inductor, capacitor, and freewheeling diode, D2. For the transformer side, what is important is that the IT2 current is 0. Now we can recall the transformer equation, ideal transformer equation, and substituting IT2 is equal 0, we can calculate IT3. That is a function of IT1. Why IT1 is different from 0? Because the magnetizing current that is flowing from the supply voltage to the ground, let's say, is positive at the end of the on phase. It cannot stop flowing, needs somewhere to go. And in this scheme, the only path for the magnetizing current is the IT1, the primary winding here. As a consequence, there will be a current through the primary winding, no current through the secondary winding, and there will be a current through the tertiary winding. This current will be negative with respect to IT1, but IT1 is negative. And this current is proportional to the magnetizing current. For the assumption, if you assume that N1 is equal to N3, this current is exactly equal to the magnetizing current. Please note that this current flow is just providing some energy to the power supply. There is then some energy storing in the magnetizing inductance during the on phase, and some energy recovery of the magnetizing energy during the off phase. In principle, this process could also be 100% efficiency. In reality, there will be losses. This is another motivation for minimizing the magnetizing current. It will reduce the power efficiency of the entire circuit. Keep studying the off phase, we can understand that the magnetizing inductance and current dictates the current into the tertiary winding. We said that there is a magnetizing current that cannot change instantaneously. Then we can calculate the IT1 current, and once we know the IT1 current, we also know the IT3 current. This IT3 winding is the key to calculate the other voltages. In fact, we can say that since the current is flowing in this direction, the D3 diode is on, and the voltage drop on the diode is 0. We can then calculate the V3 current, V3 voltage. That is exactly with this convention for the voltage. V3 is exactly equal to minus Vi. Once we know V3, we can calculate Vp, the primary voltage, that is negative, minus N1 divided N3 Vi. Again, if if N1 is equal to N3, this is more or less equal to minus Vi. The transistor voltage will be 1 plus N1 divided N3 multiplied Vi. and the secondary voltage will be negative. We expect that this is negative since this diode is off. In this condition, the magnetizing current decreases linearly since the voltage on the primary winding is negative, and it is equal to minus N1 divided N3 multiplied VI. We can then write that the magnetizing current will decrease from the maximum to linearly with a negative derivative that is proportional to N1 divided N3 multiplied VI multiplied T minus TO divided the magnetizing inductance. At a certain point, the magnetizing inductance will go to 0. When the magnetizing current that is flowing in this direction goes to 0, in principle, if everything was dictated by this inductor, it could go negative. If the voltage keeps being negative, the current could go negative. But a negative current here means also a current negative in 83. And this means that this diode should conduct in the other direction. This is not possible. This means that when the magnetizing current reaches 0, IT3 is 0, IT2 is 0, and also IT1 is 0. All the currents in the main transformer, are 0. The transformer is completely discharged, you can say. And we can calculate the voltages in this third condition, that is the off phase with 0 magnetizing current. Now there is no voltage here. VD3 is equal to minus VI. V3 is equal 0. Vp is equal 0. Vs is equal 0. And the transistor voltage is just Vi. The complete plot for current and voltage behavior is then. We studied the behavior during the on phase up to this moment. At this time instant, the switch goes off. The transistor voltage becomes positive because the transistor is blocking voltage here, and it becomes larger than Vi. It becomes 1 plus N1 divided N3 Vi. The primary voltage, that is Vp, becomes negative. This also can be larger than minus Vi. The secondary voltage is the blue one, is also negative. The tertiary winding voltage is negative, and during this phase, the negative voltage on the primary winding, Vp, causes a negative current flow, a negative derivative of the current behavior for the magnetizing current that we can see here slowly goes to 0. In this plot, it is also shown IT3, that is the current in the tertiary winding. It goes from 0 to positive, and it is proportional to the magnetizing current. And it is also shown IT1, that becomes the negative of the magnetizing current and goes to 0 with the magnetizing current. The current IT2 goes to 0, and the switch current goes to 0. After a certain amount of time, the magnetizing current goes to 0, that is, the transformer is completely discharged, and we can see that the voltages behave accordingly. The transistor voltage goes to Vi, primary and secondary voltages go to 0, and the D3 voltage goes to minus Vi. Similarly to the flyback, as previously said, we do see that during the off phase of the switch, the 3 voltage, the transistor, needs to sustain a voltage that is larger than the supply voltage for certain amounts of time. In the previous plot, I showed you that the magnetizing current is charged during the on phase and discharged during the off phase. In principle, no one tells us that there is enough time to discharge the magnetizing inductance. We are not imposing any constraint on this. It's not like the inductor current that we are imposing is equal at the beginning and at the end of the switch, and then we calculate the out voltage. In this case, we are not imposing anything, and it could happen that the current does not go to zero. We need then to impose that the current then has enough time during the off phase to be reset, to be set to zero. We need time to discharge the transformer. The equation that derives from this need is that N1 divided N3 multiplied Vi during the off phase divided the magnetizing current is larger than Vi T-on divided the magnetizing inductance. Which is what this equation tells to us. This is the maximum of the magnetizing current during the on phase. This is the maximum discharge that we can get, because the discharge rate is proportional to N1 divided N3 multiplied Vi Lm. The maximum discharge that we can get is N1 divided N3 multiplied Vi divided Lm multiplied the off time. This is the maximum discharge, and this must be larger than the maximum charging time and the charging rate of the magnetizing inductance. Substituting to T off 1 minus T on and divided by capital T, we get the limit on the duty cycle. That tells us that this equation needs to hold, and then the duty cycle must be smaller, and we get a maximum duty cycle that is equal to 1 divided 1 plus N3 divided N1. In order to minimize the leakage inductance between N1 and N3 windings, like we have seen for the flyback converter, a common choice, and as I told you more than once, a common choice is to set N1 equal to N3. This means that I can bound together the two wires, minimizing the inductance, the parasitic inductance between them. In this case, the maximum duty cycle for the forward converter is 0.5. The duty cycle can increase if N3 is larger than N1, but this is not a very common choice. We can understand that we can increase the duty cycle, increasing N3 divided with respect to N1, because the discharge rate, as you can see, should be proportional to N3. Maybe there is an error here. No, it's the opposite, sorry. If N3 is smaller than N1, because the discharging rate is proportional to N1 divided N3. If N3 is smaller, the discharge rate is faster, and we can discharge this inductance much faster. The point is that the primary voltage depends on N1 divided N3. If N3 is small, this primary voltage becomes very large, and it will discharge the magnetizing inductance faster. This concludes our analysis of the Flyback converter. We can complete the analysis using a simulator, using the simulator to see what happens in a real circuit. We can now keep studying other aspects of the circuit. I want, for example, show you a possible design algorithm for a Flyback converter, for a forward converter. This is obviously not the only design algorithm, because obviously it will depend on the input constraints that we have. However, imagine that we want to design a forward converter that will work in CCM, in continuous carrier mode, and imagine that, as it is common, we have data regarding the load, that can be the resistance or the current that the load needs, the output power. We know the supply voltage, and we also know, and this is quite important, minimum and maximum values for the supply voltage. Imagine that we know the switching frequency, because it will depend on the device that we have. We also assume that we know the maximum duty cycle that we can use. Imagine that we are using a forward converter with tertiary winding, and we have N1 is equal to N3, the two windings have the same number of turns. This means that there is a limitation on the duty cycle that is 50%. For practical reasons, we don't want to destroy the circuit. We want to limit, for example, the duty cycle to 0.45. Okay, these are the data. We can start designing what we need to choose. Since we know the switching frequency, we imagine that we know which device to use. The device is known. We don't need to select the switch. Imagine we also don't need to select the diodes and D3, D2, and D1 diodes. They are known. We need to choose the output inductance, output capacitance, and the transformer. For the output inductance, we know which is the average current in the inductor, because the average inductor current is the load current, and we know the average current into the inductor. If not set from the specifications, we can set a ripple like 1/20th or 1/15th of the average value, and then dimension the inductance value. For the capacitor, the sizing is always the same. Once we know the inductance value, the capacitor size will determine the ripple on the voltage, on the output voltage, or maybe we have a constraint on the load changes and the amount of voltage overshoot or undershoot on the voltage when the load changes. Hence, this will allow us to determine the capacitor. For the transformer, the first thing we need is the magnetizing inductance. We want it large because we have seen more than once that this magnetizing inductance is a problem, will provide us issues and also efficiency reductions. A common choice is taking a magnetizing inductance that is 3, 5, 6 times the output inductance value. As you can see, in this, let's say, algorithm, a number of unwritten rules are used, like the ripple is 1/20th of the average value, the inductance is 5 or 6 times larger than the output inductance. Obviously, these are unwritten rules that are quite always useful. It is obvious that if you have an output inductance that is X and maybe has the size of 1 centimeter cube, something like this, you cannot imagine to use a magnetizing inductance and transformer that is 100 times larger. It will mean a transformer that is 100 times bigger. Hence, I want a small magnetizing inductor for most practical applications. 3-6 times larger than the output inductance is okay. Choosing the magnetizing inductance is one important point. Another important point is which is the average or maximum current into the core of the transformer, because there is a limit on the current that the transformer can handle. Above a certain current, the transformer saturates and the core hence behaving like a magnetic core, and this is a real problem for the circuit. We can then calculate the average, the supply current, with simple assumption on the efficiency. If we assume a given efficiency, let's say 90%, 80%, or maybe 100%, we can say that the supply voltage multiplied by the average input current is equal to P out divided the efficiency. Hence, we can easily calculate the average input current. That hence the supply current will be the output power divided eta multiplied VI multiplied the duty cycle. You can study the forward converter to convince yourself that this equation is okay. Once you know the magnetizing inductance and the current, maximum current into the transformer, you can design the transformer. You can select a pre-built one or design one yourself. There are well-known algorithms that are not detailed in these lectures. You will study it later. Once you know the number of turns and this design will tell you also how many turns you need for the primary winding, N1. Now you can calculate N2. Okay, this is the last thing that you need, and you can calculate this one imposing that the output voltage will be equal to VI multiplied duty cycle divided N2 divided N1. In this case, it is better to use the maximum duty cycle that you can get multiplied by the minimum voltage, because in this case, this is the, let's say, the worst case that you can get. Once you know N1 and N2, N3 we said from the specification that is equal to N1 since the maximum duty cycle is 0.5, is 50%, and the design is more or less closed in principle. This concludes our study of the forward converter. As previously said, we just need some more simulation to understand the behavior of the circuit. The switch mode power supply field is very large. There are many topologies that have not been explained here. In particular, I did not explain the higher power topologies like the push-pull or the bridges. Just some small example. Another topology that can be used in the switch mode power supply is the two-transistor forward converter. The circuit that you see here is quite similar to the one that we studied. In the output part, for example, is it's the same. We have D1, D2, the LC filter, and the output voltage that is connected to the load. And here we have the transformer. The two dots are in the same direction because there is a direct transfer energy or transfer between primary and secondary side. The switch is here. Everything is like we expected. The differences are this second transistor and these two diodes. In these two transistors forward, the two transistors need to be activated together. They are on in the same time. When both devices are on, the current flow is from V in to the tier 2 through the primary winding and through tier 1. While the current flows, it is charging the magnetizing inductance, obviously, and there is a current and energy transfer on this other side. Up to this point, almost no difference with what we studied for the forward converter. The only difference can be there is another voltage drop, on-state voltage drop on the upper transistor with some added energy losses. Okay, but in principle, no real differences. The big difference is when the devices are off. In the off phase, both tier 1 and tier 2 are switched off. There is no current flow through the transistors. The secondary portion of the windings are off. And we have the problem with the magnetizing inductance. How can this current keep flowing, magnetizing inductance that is charged? We know that there is a current that flows from top to bottom here. But since there are these two diodes, the current can actually do this path. Starts from the ground, passes through this diode, like D3 in the forward converter with tertiary winding that we studied, flows through the primary windings, and then passes through this fourth diode, let's say D4, and is again back into the power supply. There is then a current flow that is again discharging the magnetizing inductance and is providing some current to the power supply. The current path is the following. Through the two diodes. Which are the advantages? Why doing all this? As you can see, when this happens, this voltage here is more or less 0. The voltage here, this diode is short-circuiting, is more or less V in. This means that for tier 1, the collector to emitter voltage is just the input voltage. It's not larger than the input voltage, it's just the input voltage. And the same happens for tier 2. Because this voltage here is V in, and this voltage here is 0. Both devices will just need to sustain the input voltage. And this is an improvement because you can choose lower voltage devices that are more efficient. And since the devices are less stressed, for the same inductance, for the same components, maybe you can provide more current. Hence, this topology is usually intended for slightly higher power topologies like the 400 watts range. However, we are paying something. Because we are paying one more power device, we are paying one more diode. These are components that have their cost on the topology. It's not free. However, you can see that small or large modifications to the circuit, leaving most of the things unchanged, are just changing the voltage requirements on the circuit and changing the power. Could you expect that the addition of this transistor was able to improve the power range of the forward converter by 25%? In principle, no, but this shows how important are these topologies and how it is important to properly design these circuits. The two transistor topology is also possible for the flyback. We have seen many similarities between a forward and a flyback converter. And also in this case, instead of recovering the energy in the magnetizing, the parasitic inductance energy with the tertiary winding, instead of allowing a flyback voltage that is larger than Vi when the output voltage is reflected to the input, also in this case we can use the two transistors with the two diodes to block the voltage on the transistors. Similar advantages and disadvantages that we have for the two transistor forward converter.